Hello everyone. So for today's video lecture, we're going to be talking about the conservation of energy for a particle. So far, we have used kinematics to relate position, velocity, and acceleration, and we've used force, mass, and acceleration method, branch of kinetics, to relate forces and accelerations. Now we're going to be using work and energy methods, another branch of kinetics, as an alternative to the force, mass, and acceleration method, where we had F equals ma. So the work and energy method provides an alternative to the force mass acceleration method. So almost all kinetics problems can be solved either way. The force mass acceleration method is going to be easier in some cases. The work and energy method is going to be easier in some other cases. And then the impulse momentum method that we haven't talked about yet is going to be easier in a third set of cases. So you really got to pick the tool that's going to be most appropriate for your given problem. All right, so what is the work and energy method? Well, the work and energy method is best summarized as the following. So the work done to a system will be equal to the change in that system's energy. And this is going to be the basis of everything that we do with the work and energy methods. A work is a force applied over some distance in its simplest form. And energy is going to be translational or rotational kinetic energy, as well as gravitational or elastic potential energy. So the potential energies, we're going to talk more about those later on. So there are other types of energies out there, but we're going to focus on these types of energies for dynamics. All right, so if we put all of those pieces together into a single equation, we wind up with the conservation of energy equation, which is the following. So this says work is equal to the change in kinetic energy plus the change in potential energy. So we're almost always going to start with this simple equation, which we're going to adapt to our situation. We put in what we know about work, we put in what we know about kinetic energy, and we put in what we know about potential energy, and then solve for the unknown variables. All right, so starting out kind of dealing with some of those terms, we have work, kinetic energy, and potential energy. So work done to a system, at least in a dynamic system, will be the force times a distance. So in this case, we've got some box. We're moving it from the point A on the left to point B on the right. And the work done by this pushing force is going to be the force, so the magnitude of that force times the distance. If we have something that goes in the opposite direction of that displacement, so like friction, for example, is fighting the motion, that's going to be a negative amount of work because the force and the distance are going opposite directions. All right, so we've got positive and negative work in this case. We also need to note that the pushing force, if we are not exerting it directly in the direction of D, we only are going to use like the x component of the pushing force here. So in this case, the work of that pushing force would be the pushing force times the cosine of theta, which gives the x component of this force, times the distance. Forces that happen to be perpendicular to that displacement, the distance traveled, are going to exert no work at all, because if you imagine cosine of 90 degrees, that's going to be 0. So the normal force in this case, it exists, but since it's perpendicular to that distance traveled, it's going to be 0 work done by the normal force. All right, so all of that goes together, and then sometimes we're also going to encounter forces that are going to change as the body moves. So say we've got some force and it's changing as I push the box. So I'd have some f of x function that describes the force at any given distance as it moves. In cases such as this, the work done by the friction force will be equal to the integral of the force function over the distance traveled, or the area under this particular curve. So work from x min to x max, minimum, maximum displacement there, and we just simply integrate the force function. All right, so all of those things are potentially part of the work done to any given body. Next up, we're going to have kinetic energy. So the kinetic energy of a body, of a particle in particular, is going to be the following. So 1/2 mv squared. M is the mass of the object, and then v is going to be the speed of the object. I'm not saying velocity in this case because the direction does not matter. So I'm just worried about the magnitude of the velocity, which is speed. All right, so in the conservation of energy equation, we have the delta Ke, though, so the change in kinetic energy. Assuming constant mass, it's going to be simply 1/2 mv final squared minus 1/2 mv initial squared. If the mass is changing, we'd have a final and initial mass as well. All right, so that is our delta Ke term. And while the direction of force was important for work, the direction of velocity is not important. So kinetic energy and potential energy both are scalar values. They don't have a direction. They cannot be broken down into components. You'll notice we just had the one equation. We don't have an x and a y work, x and y kinetic energy. And kinetic and potential energies also cannot be negative. So I can't be going slower than 0 speed. But I can have negative changes in energy. So I can have a large kinetic energy and a smaller final kinetic energy, and that delta Ke could be negative, though. All right, moving on to potential energy. So potential energy has many forms, but in this course we're going to focus on two. We're going to have gravitational potential energy and elastic potential energy. So gravitational potential energy, the change in gravitational potential energy in particular, is going to be mg delta h, where g is our acceleration due to gravity and delta h is the change in height of the object, so it either moves up or down some amount. And then elastic potential energy is going to be 1/2 kx squared, and then so delta Pe would be the x final squared, x initial squared for our system. So that K is the spring constant for our spring. So the stiffer the spring, the higher that K value is going to be. It's going to be something inherent to the spring we're using. And then the X value is the difference in length from the resting length. So say I had a 5-inch spring, and if it's, you're just sitting on a table, it's 5 inches long naturally. If I stretch it out by 1 inch, the new length is 6 inches, but that X value, it's 1 inch because I've stretched it by 1 inch or compressed it by 1 inch. All right, so those are the two types of potential energy. And looking at gravitational in particular, gravitational energy is not really an energy at all, same thing with elastic, but instead represents the work, so the work that the gravity force would do as the body moves. So if I've got this block, I imagine lifting it up some delta H value. I've got gravity fighting me that whole time. It's going to be mg is the magnitude of that gravity force. So the work done by gravity would be negative mg delta H. So it's negative force times distance. It's negative because they're going opposite directions here. So when we switch this over to potential energy, when we go from the work side to the energy side, the negative sign disappears because we're basically going to add the same quantity to either side. All right, so elastic potential energy, now if we deal with that, elastic potential energy represents the force, the work that a force is going to do, or a spring force is going to do to a body as we move the spring. So imagine we have a spring, it exerts a force on a mass as shown, so it travels from point A, which is the point shown, to point B. So as I move it, so I'm compressing the spring in this case, the force of the spring is going to be that spring constant times whatever my current displacement is. So the more I compress the spring, the more force I get out of it. So the force is K times X, and I'm moving it some distance X. All right, so to find the work done, since the force is not constant, we need to take the integral of that force function. So the force function itself is Kx. It's going to be the opposite direction. That's where that negative sign comes from. I'm going from 0 displacement up to some x displacement in this case. And so I wind up with negative 1/2 kx squared because the integral of negative kx dx is going to be 1/2 kx squared. All right, so that is the work done by the spring going from 0 to some distance x. And then the negative disappears again when we move it from the work side over to the energy side. All right, so both gravity and spring forces are also known as conservative forces. And so what that means is the exact path taken is not important. Just the change in height for gravity or the change in length values, that difference from the resting length for springs. So for example, we've got this ball and pendulum on the right. So I've got a ball on the end of a string, and I release it. It's a pendulum. I just release another one. It's not attached to a string. All that's going to matter is the delta H. And so the reason we get away from this, so even though the pendulum moves a lot further, the gravity force, only the perpendicular part is going to count. And so as this moves further, there's only a section of that, the work done by the gravity, that's actually exerting work. Whereas here, it'd be force times delta H. We get a pretty simple relationship there. But in the end, delta H is all that matters. And then for springs, like I said, the change in X value is the only thing that matters. All right, so putting this all together, solving a work and energy problem, the process we're going to run through with these problems. So it involves 3 steps, and we need to carefully account for the factors at play between some initial state and some final state. So step 1 is going to be a diagram. So it's not necessarily going to be a free body diagram, but we do need to show an initial state in one diagram, and we want to show the final state in another diagram. Identify any forces that are going to do work between the 2 states. We want to identify any known or unknown velocities. So I might know the initial velocity, but like not the final. Identify any change in height. So identify the delta H if applicable. And identify any X values for the initial and final values if applicable. Again, you're not always going to have a change in height. You're not always going to have springs in these problems. But if you do, you need to identify those in your diagrams. So after we get the diagram, we get everything set up, we've identified our known and unknown values. We're going to use the diagram to put together a single conservation of energy equation and include the known and unknown values. So that equation is, again, is work is equal to delta KE plus delta PE. Plug in what we know for each of those pieces. And if you have more than one unknown, because when you have one equation, we're going to need to come up with additional equations relating the unknowns that you have. Change in height might be related to your X values if you've got a spring in there too. So you can figure out geometry-wise how that relationship works. And then once you have enough equations, you simply solve the equations for the unknown quantities in this whole thing. All right, so with that, that's all we've got for today's video lecture. Thank you for watching, and I hope to see you again.